Okay, good morning everyone. My name is Matthias. I'm presenting with Jan. We're going to talk about VMware NSX. How many of you have heard of VMware NSX? It's about 50%, I'd say. Okay. All right, we will still do the introduction. I won't force you to give a definition, but we will go through it. So our talk, basically, we will give you a technical overview of what VMware NSX is. We're then going to analyze its attack surface, give you an overview of its attack surface, and also the implemented security controls that are already built in. After that, we perform attack surface evaluation, and then want to give you an introduction on how to actually perform security assessments in the NSX ecosystem. This is going to be hard for me. I usually like to move around and point on the slides. I really hope I stick to the microphone here. All right, as a first introduction, this is Jan.
We got a microphone.
Awesome.
Yeah, hello, my name is Jan. I'm a security consultant at ENW, a German company. Oh yeah, he didn't said we are from Germany here. So.
Oh yeah.
Working as a security consultant. Former I was working as a security analyst, pen tester, or you can name it also web app monkey during the time. And so there's always changes progress, so we must change. I did my master degree at the TU Darmstadt at IT security. And yeah, my interests are bug bounty, red teaming, social engineering, and in my free time, if I have some, camping and music festivals.
Okay, as I said, my name is Matthias. I'm a freelancing IT security researcher, consultant, trainer with like my main focus on penetration testing, virtualization security, network security, and recently also, let's say, the agile security space, cloud containers, and so on. So what are we going to talk about today? As I said, we want to give you an overview to VMware NSX, and particular VMware NSX for hackers, so for offensive security research. We have a focus on the attack surface and how to actually perform security assessments. What we're not going to do is like give you the, let's say, infrastructure sales pitch, what security designs you can do with NSX and which security features are built in there. So why are we doing this? Why are we having this talk? So when I talked to Rodrigo, what we could do talk-wise, I told him, oh yeah, we're performing this project at the moment. We have not found any vulnerabilities yet, but as you know, modern technologies are often incredibly complex. I'm pretty sure we'll give you an idea how complex NSX is in this talk. And this complexity does not necessarily mean it's super difficult, as in like NP hard, but it's a lot of big, intransparent, closed source components. And it's actually really difficult to get an idea from the vendor what a component or even like the overall product is doing on a very technical level. So, I mean, this fact that we have so much big, complex technology is often killing security research before it can actually take place. For example, for us building the research lab, that took like more than 10 person days to set everything up, to get the components up and running. And after that, we were able to perform some research. And this was not even the full scope yet. So during the talk, you will see the components that we already analyzed and have up and running. And that's by far not the full functionality yet. So it is very, very difficult to build such a lab. If everyone that wants to do security research on NSX has to do that, you can easily do the math, like how many person days that would be to just get the lab up and running, and then you're usually out of research time, right? I mean, who of you has on a persistent basis more than 10 research days? So basically, we want to give you like clear instructions how to build a security validation lab if you want to perform any offensive validation. I also have this nice quote from Halvar down here where he said the most expensive security appliance is the most secure security appliance, because nobody has the money to buy one and just play around with it and identify vulnerabilities in it. I think the same holds true for complex technologies. Actually, this lab, as like a first information, is not, let's say, from a licensing perspective, it's not hard to build. There's evaluation licenses for ESXi and also for like the hypervisor by VMware. And for the NSX components, you can also like buy a rather cheap evaluation license for NSXT. So basically, if you want to do the evaluation, the licensing won't be a problem here. So that's the first relevant information. So, we're going to start with a technical overview. Now you understood the scope of the work, and we will give you the rundown of, let's say, NSX for hackers.
Yeah, just
So,
okay, we will continue with a technical overview of NSX. How is it built? Now, at first, I will shock you because we have NSX. It's a huge combination of different components, and basically we have a manager. Just start from a perspective. We have the physical layer, means the hypervisors in the ground, physical machines or vSphere, and on top of it, we have the virtualization layer. NSX is split into AP services managers and different kind of components with, which I will focus in the next slides. On top of it, you can combine it with different cloud providers. You can combine it with OpenShift or, for example, Kubernetes and virtualize the network infrastructure with it. So, as I mentioned, VMware NSX is a hypervisor agnostic virtualization layer for network components with the probability for micro-segmentation and filtering. So you can on demand define layer 2 domains and debuild them also. The idea is to decouple the networking functionality that's actually at the moment built on the wire at least, on the physical layer, and we want to use a virtual version on it on top. It's like an overlay. Interesting part of it is that the whole system is API driven. So after you've configured once and you have get used to it, you can configure it later on by API calls and define further network components on demand and schedule it up and down. The difference, NSXT is the part that NSXT is dedicated to be hypervisor agnostic. So you can run NSXT also not dedicated with ISXE or vSphere. You can also use a KVM system on the ground. Okay, I mentioned there are a lot of different components. How they are later on configured and communicating with each other, I will come to. But we will go to the major components at first so that you have an idea what's the functionality of them. So we were just monitoring and just analyzing the systems that we have. Okay, we have the NSX Manager. The NSX Manager is for you guys or for the administrators, the interface where you configure and define your networks and your virtual infrastructure. The interface offers a UI like a web interface or even the REST API to automate it. If you run into troubles, you can also use it to monitor all the service and for debugging purpose. It's important to say that we have only one manager. You have one dedicated point where you have to configure the whole infrastructure. That's kind of an advantage and it helps a bit. Just, I would say, a bit. For each step, I have one. The communication of the NSX Manager to the other components is by via the management plane agents. All management stuff is done by this agent. We have different kind of planes. I will come later to this part, to the management plane and the plane stuff. But for now, you must keep it in back. You have a management plane agent on these managers. In addition to the management device, you have controllers. The NSX controllers are kind of a distributed state management system. And these controllers are to enforce the defined policies and devices. So you configure your network in the manager, and this information is forwarded to the NSX controller, to this distributed state management system. And this point will enforce the configuration on the hypervisors that you will instrument and which you will have configured with NSX. It's responsible for just deploying the new virtual networks. The NSX controller configures on the combined hypervisors the tunneling endpoints. So you have the hypervisors, and they must somehow know which other hypervisors are they connected to, and it's part and the job of the controller to manage it, establish virtual tunneling interface endpoints, and so on. You must keep in mind the controllers are independent on the later on overlay network. If the the NSX controller goes down or is not contactable or reachable, the data plane between, I will come later to the planes, the data plane, the traffic is not pushed through the controller. An additional information for you can have multiple NSX controller to have redundancy in the system. So if one controller goes down, you have another one who will keep backup and support you. In addition, NSX is just a visualization, an overlay, a virtual network layer for communication. And to get out of these networks, this virtual network layer, we have Edge, the NSX Edge. It's a connection to the external network. In one setup, you can have multiple Edge devices to ensure you have a connection to different external networks. As I mentioned, you control with the NSX controller the different hypervisors. And these different hypervisors are connected with each other in one transport zone. In this transport zone, each hypervisor is a transport node and has a dedicated network interface. They are somehow connected with each other in virtual tunneling endpoints. So the communication between the hypervisors is all in the transport zone, and they are transport nodes. And it's communication, the virtual network overlay. In the controller, you use it to configure logical switches and define on the physical location more independent layer 2 broadcast domains. Means you have spanned over the network zones different devices that participate with each other, and you can have a single layer 2 broadcast domain, and you can segregate dedicated and flexible. Another part of the NSX components is you have logical routers where you can define 2D architectures. Can imagine you have a north-south connectivity where the north part is the NSX edge where you have the connection to the physical network, and on on the south connection you have an east-west connectivity to separate the networks there. The information between such logical routers is exchanged over the control plane, the information, yeah. And there's nothing like, BGP, you name it, OSPF, for exchanging the routing information. Yeah, the management is done by the management plane. Okay, all the planes I talked about, at least there are only 3. The first plane was the management plane where you configure it. Then you have the control plane where the configuration are exchanged and forwarded to the hypervisors, and the hypervisor establish a data plane. And this is the general overview of the components we actually analyze in our talk. And Matthias will now continue and define the attack surface.
So those were like the less interesting basics that you, however, still need to know to understand the whole thing. I'm pretty sure you get an idea how much more fun it even is to extract this information from the VMware documentation. So all the terms that we heard now, let's translate that a little bit into a technical attack surface. However, I wasn't quite sure where to put this in the talk, but as a small, let's say, tooling methodology input, typically when you want to analyze such a closed system, you have the challenge that you want to jailbreak this system. So for example, if you have a physical security appliance, you usually boot up, you have a web interface, you sometimes have like an SSH interface, but then there's like a custom command line interface that doesn't really let you do anything, and also doesn't let you access the underlying file system. So since all the appliances and also more complex closed system are moving to virtual versions, so you get basically VM with a virtual appliance on it, it's usually very easy to jailbreak that stuff. So basically you can boot a live CD in it, you can just mount the virtual hard drive somewhere else and then access the file system. If that for some reason is difficult or hard, it's also always possible to edit like a memory dump of a suspended virtual machine. So for example, you pause the virtual machine, edit the memory dump with a hex editor and just replace one command line call with another one to, for example, some bash call or some connect bash port. Then we also have a virtualization-based debug port that you could use in the very worst case. We will describe that later. Or what's also always fun and the first thing to try, if you have a command line interface, you can also find let's say like a breakout opportunity. There's a very good repository of Linux binaries that have additional command line switches that you can use to supply actual shell commands. So in the case of NSX, both the manager and controller VMs are Ubuntu VMs with very large Java services on them, which we'll describe later. And they have a root maintenance account where you actually get dropped to an actual bash. So that was very easy to achieve here. On the ESXi, you also have SSH access with a somewhat decent shell. So jailbreaking NSX is not a problem, but I still wanted to include that information since closed virtual appliances can sometimes be a bit tricky to analyze. So let's look at our attack surface. As already described, we have a data plane, we have a management plane, we have a control plane, and then there's something that I called SDN services. I apologize in advance for using such a buzzword, but I couldn't come up with a better term so far. What we're not going to talk about is traditional VMware or vSphere attack surface. There have been talks in the past. I still think this topic is underrepresented, and I think there might be some juicy bugs still in there, but this is not the focus of this talk. So we're not talking about attacking vCenter via the HTTPS interface or the 902 management port of VMware. It is interesting, but not in scope of this work. So let me describe the different planes on a more technical level to you. This is a smaller part of our test setup. You can see here that we have two ESXi servers that are basically part of our NSX environment, and we have two virtual machines running on them. Now we have the blue part here. This is our generic layer 3 IP transport. So basically the two ESXi hosts have two interfaces that can communicate via IP. So if you have now different virtual machines in there, their communication is not, I mean, technically yes, but not like IP-wise carried out via the IP transport. So basically the two ESXi servers establish a tunnel. The details of this tunnel will be described later. And then the actual communication is carried out via tunneled IP traffic. So why is that helpful? Why do we even need this? Jan described it a bit earlier. We want to virtualize the network and be somewhat more independent of this generic IP transport. Very simple description. So you have two ESXi hosts. That's quite a simple scenario. If it gets more ESXi hosts, as in typical deployments, it gets more complex. So you have two virtual machines here that run in the same subnet. Easy to configure. However, if you want to have an additional machine in this hypervisor and an additional machine in this hypervisor that are like located in a new, let's say, network segment, then in the traditional world, you had, like on physical network devices, you had to configure additional VLANs, add those VLANs to the trunk to the ESXi host. So basically, you had two worlds that you had to maintain, the, let's say, physical network world and the hypervisor world. Now, in this scenario, everything can be done on the hypervisors, or let's say on the virtualization environment. So you don't have to do some physical configuration on switches to add VLANs, adjust routing, or anything like that. Basically, all of that can be done in here, and that's all doable via API calls. So question, this is the reason that this is pushed is for like automation and orchestration reasons. So those are the technical details of the data plane. The data plane is implemented as a kernel module on the different ESXi hosts. We will talk about these kernel modules later. The Genève protocol as well, this is mentioned here for now. I think the one interesting fact is that even the listening port for the tunneling is completely opened by this kernel module. So we keep that in mind for later. So this is the implementation of the control plane. We have technically two kernel modules communicating with each other via UDP on port 6081. Then we have the management plane. As Jan described, the management plane is basically the web interface that we have here. So as a user, you connect to a web interface on the NSX manager and you configure your environment. All those configurations are then stored somewhere, and configuration changes are pushed into a message queue. This message queue is listening on TCP 5671, so slight differentiation from the message queue standard port. And then the NSX controller is pulling this information or pulling messages from this queue on a regular basis. This is taking place in an authenticated, encrypted way. This is usually negotiated TLS cipher suit, which is interesting because it doesn't have PFS enabled. I wouldn't say that's a finding. It's still like a decent cipher suit, but that's the point just for mentioning it here. So this is the management plane agent that Jan mentioned earlier. This is basically running on any component that we will see later, and it's pulling the information from this message queue on a regular basis. Then we also have additional, I forgot to change the subject here. This is basically the centralized control plane. Sorry for that. This is not the management plane anymore. Management plane takes place over here. So basically the NSX controllers get configuration changes from the management plane, and then this configuration changes may result in changes to the central control plane. So first of all, there's like a cluster service that is used to maintain cluster state if you have a cluster of NSX controllers, which is running on port quad 7. And then we have the CCP, the centralized control plane service. This is running on port 1234, easy to remember. And then we have a CPA, a control plane agent on the different transport nodes that is then pulling information from here again. So the transport nodes are, as Jan described, can be ESXi hosts, can be also some types of virtual machine. For example, NSX Edge is also called a transport node in here. So this is basically the overview of the management plane. There's one additional feature. There is a software download interface on the NSX manager, which is listening on HTTP port 8080, and where certain components are sometimes downloading software from. So then we have the SDN services. As I said, sorry for the buzzword, I didn't have a better term for that. The SDN services are, let's say, the actually interesting part of NSX. I mean, it's very great to configure basic network connectivity, network forwarding between subnets. It can be already very helpful if you have a bigger cloud-like environment and you want to deploy whole application environments in an automated way. However, these features are the actually interesting ones because, for example, you have firewalling modules. You can do flow tracing between different virtual machines. You can do advanced routing. You can actually implement like load balancing in there. So those are all additional services that make this environment actually interesting. So the firewalling, for example, allows you to implement microsegmentation. Also here, not going into architectural details. If you want to discuss those, I'm more than happy to, but we don't have the time for this. Actually, here it says this functionality is implemented in various kernel modules. Let's say most of this functionality is implemented in kernel modules. We choose this information because the features that we have so far to analyze, they were all implemented in kernel modules. Stuff like load balancing, for example, also has a lot of like userland components, but this was not in our lab setup yet. So those kernel modules are basically listed here. All of those modules are like between 28K and up to 1 megabytes in size. And I just want to go over some of them to give you a better idea. So if you want to connect virtual machines and give them Ethernet connectivity, you obviously need a virtual switch. We have two kernel modules that basically implement layer 2 connectivity, including some logical structuring. So we're not really using the VLAN term in here, like in the traditional vSwitch environment. We're using this logical router and logical switch terminology. And so the logical switching is implemented in here. Then we have NSX switch security, we have NSX traceflow. Traceflow is actually a module to analyze the network flow between two virtual machines. So it has a lot of troubleshooting functionality involved. We have NSX IPFIX, that's the flow export, if you want to export flow data for your environment. And we have NSX DNA, which is distributed network encryption. This is another functionality that is very interesting. Basically, it implements the functionality to have your network traffic between two virtual machines encrypted. So not between two hypervisors, but really between the two virtual machines, end to end. So if we break this down by component, we have on the NSX controller, we have the cluster RPC, which is listening on TCP Quad 7. We have the centralized control plane on TCP 1, 2, 3, 4. We have the NSX manager with the user interface and the API on HTTPS. We have the message queue on the also part of the management plane, and we have this update repository. Also, we have on the transport nodes the UDP 6081 for the virtual tunneling, and we have various kernel modules inspecting network traffic. Some of those kernel modules, like the firewalling module, they have to inspect all traffic, which of course is super interesting from an attack surface perspective. And this is what we're going to talk now about. So if we wanted, when we wanted to prioritize our research, we try to understand the whole system first, and then basically see what has the most interesting opportunities for attacking and exploiting it. So the NSX design guides clearly recommends to separate the control plane, management plane, and basically all the planes on the network level. So this is an extremely good recommendation, and I urge you to keep that in mind when you do that. But that also means that all the fancy services listening on TCP, like the message queue, the CCP, the MP, all of those you usually won't be able to access if they are properly isolated on the network level. So you can't access them from within virtual machines, you can't access them from a client network. That should be strongly isolated towards a management network. So that drastically reduces the actually available attack surface here. Then again, the control plane and also the management plane is also like implemented using TLS and proper authentication, so there's no low-hanging fruits there. In addition, there are many more services running in there. I mentioned in the beginning that those appliances are basically Ubuntu VMs with very large Java services on them. A lot of those services are only running locally or, for example, for the NSX controllers within the controller cluster. Was that a question? Okay. So basically, for example, we have a Zookeeper instance running in there. However, it's not really available on the network. It might be interesting local attack surface, but it's not available on the network. So not very exciting. I think I hinted towards that several times. The transport node kernel modules provide the most interesting attack surface. They have a very high exposure. They basically need to inspect all network traffic going to the virtual machines. So, of course, you can attack virtual machines via the network, but it might be even more interesting to just send malicious traffic to a virtual machine, which doesn't even need to actually receive it or process it, but the kernel module sitting right in front of that virtual machine is processing it. And if you find a vulnerability in there, it is amazing. You can basically exploit that from any network position. Then, of course, probably some of those have very high complexity levels. Like implementing a firewall shouldn't be that complex anymore, but there's still firewall vendors that get remote code execution vulnerabilities via TCP packets. So this might be interesting. Then the distributed network encryption. This is probably a very, very complex kernel module implementing all the encryption protocols. There might be something very interesting in there. And then, of course, I said it's kernel modules, so it's pretty much the highest privileges that you can gain in a virtualization environment. So I don't think it gets any better than, let's say, kernel access on the hypervisor. So those three aspects just make the kernel modules the most interesting attack surface, and also show a little bit the methodology, how we usually evaluate this attack surface to decide where we're going to look at first. So having made this decision, there is now like quite some insight into how you can actually analyze this environment.
Exactly. Exactly. As Matthias mentioned, there is a lot of attack vectors that we can focus on, but the most interesting part would be the kernel modules. For this, we built a lab environment with a server. It's just a HP server with 32 gigabytes of RAM and 190 gigabytes of disk space, and on which we installed an ESXi server that we can virtualize our hardware that we will later on come to. The problem is the NSX manager and the NSX controller are network appliances that come from basically with 100 gigabyte disk space they need. And we ran into problems during building the setup, but we was limited. So to do the math, it was a problem, but we get used to it. For this...
Sorry to jump in.
Oh.
Sorry to jump in. I mean, you already see that this is also like a lab setup that is probably not everybody of us is sitting around at home. So even that is already difficult to set up. So that's another hurdle you have.
Okay. On this outer machine, we installed an ESX server. I would call it outer ESXi. And for this, we want to analyze the kernel modules of the ESXi server. So we must somehow get a debugging interface. And this is the reason why we thought, okay, it would be an idea to virtualize the ESXi server to debug them. And so we installed on the ESXi server 2 additional ESXi server, which run a virtual machine. In addition, we have the NSX manager and the controller. You see it here, and connect them over a virtual switch. In the configuration setup, we defined the Genève tunnel here, so that these virtual machines, VM1 and VM2, can communicate and exchange data on layer 2. As I mentioned, we want to debug the kernel modules, and for this, ESXi provides a debug interface for GDB that you can debug with GDB your virtual machines. So we configured in the inner ESXi server, in the VMX file, in the configuration file, definition that a port is exposed where you can plug on your GDB debugger on your debugging system. Before you can start the machine, you must, debug it, you must configure the firewall on the outer ESXi server that you can connect on. And in addition, for sure, you must disable KASLR to be sure that the components are always mapped to the same address in memory. That's also a configuration that you must set in the ESXi. To continue, to have a fully debug setup, it's useful to have debugging symbols so that you don't have only the binary code, so you want to have also some symbols. And for this, you can download the the Eclipse plugin for VMware Workbench. And in the dashboard, you can authenticate with your user credentials and go to the point debug symbols for kernel, and for there you can search for your build number, and then you can download an RPM package. And in this RPM package are the symbols. It's like, find it, yeah? It's not easy. And from there on, we can check on the outer ESXi server where the kernel modules for example, the NSX vSwitch are loaded into memory. With all this information, we can start our GDB and connect to the hypervisor, and load previously the symbols of the hypervisor modules. And with this, we are able to jump into the kernel modules and check out the actual stack that's on the ESXi server. You can see we are able to see the current stack. And why we do all this stuff, as Matthias mentioned already, the layer 2 packages are processed in the kernel modules. And this offers us, as an attacker, into another position where we can attack the kernel, the hypervisor level. And to analyze or attack the kernel modules, we used Dizzy. It's a fuzzer where you can implement your own fuzzing modules. And so we wrote a fuzzer for ARP. Normally you say, oh, what? A fuzzer for ARP? No one will do this because fuzzing a layer 2 and ARP protocol is normally implemented on the network interfaces. But now ARP is implemented in kernel modules, and it gets more juicy and maybe more interesting. Yeah, Dizzy is, as mentioned, a network protocol fuzzer developed by Daniel Mende, and it's extensible. We wrote a module for it, and the way you can define, for example, here is a protocol definition from the RFC grabbed, and you can define the different fields in the protocol with size and length and how to fuzz them. I will not go deeper into it. So we started a module and start fuzzing the environment. And this is how we have, for now, launched on a virtual machine on-site the inner ESXi server, the fuzzer. If we run now into a crash, we were able, with our debugging setup in GDB, to debug the current state of the stack and analyze and go and develop a layer 2 exploit for the hypervisor and try to exploit the kernel modules. Another part is the Genève tunnel. The Genève tunnel is to exchange the data and the information between the hypervisors. And if we look into the RFC, it's just actually a proposal. It's not a finalized and released RFC. They recommend at this location already, you should encrypt or separate the tunneling connection from the normal network. And so we did. We built up our setup and want to inject some package into the Genève tunnel. And so it's kind of overwhelming for a moment, but that was the setup, how we try to inject the packages into the Genève tunnel. We have the ESX1 and the ESX2 and the inner virtual machine 2 and 1. In the physical network where we have the tunneling protocol, the tunnel is established, we have the external interfaces of the ESXi server, and these are the transport node interfaces for the transport zone, where the tunneling and the forwarding of packages on kernel module level occurs. And now we are going from a attacker perspective, like a Keller machine that's on the same layer network, and have a packet crafted in the name of the inner Ubuntu machine, which should be sent from this machine to this machine. And we wrapped it in a Genève package. And now, from now, what would you expect in a secure environment? Only the transport nodes should communicate with each other. And from now, we set this frame around, and it's an UDP package, and it's not authenticated. We were able to send from the Keller machine a package in the name of this transport node to this transport node, which is at this location extract, forwarded to the machine, and this machine thinks, oh, hello, it's a package from Ubuntu 2, and answers it. So we were able from outside, from management network perspective and control plane network perspective, able to inject packages. In general, the idea is that we inject the package, it's processed on the hypervisor, forwarded to the machine receives it and say, okay, I will send an answer, and it's transmitted through the tunnel and sent to the other machine. So by now you can see from outside, if you have no dedicated separation between the control network and the legit network, you have a big attack surface, and you can attack all kernel modules on this way from this perspective. We build up this also as a setup, And you have on the left side the kernel machine, here's the Ubuntu 1 and the Ubuntu 2, and here's the spoofed package sent to this machine with answers, and the response is sent to the other machine. So this is our setup, literally. Yeah. Matthias, may you conclude us?
Yes. So, what conclusions to take from that? As I mentioned in the beginning, when we designed this talk, it was mainly like, okay, we're analyzing it at the moment. I'm more than happy to give an overview of the methodology and how to tackle such a complex system when you want to perform security evaluation. So I give you a little bit more of an overview, what we did, what potentially worked, what didn't work yet. So what we didn't even set up yet, because that would have taken even longer to set up before to start the research, is like clustering with all the clustering components. You can also have those edge interfaces, edge systems or edge nodes that can be clustered again as well. So the edge systems are also very interesting attack surface in NSX, because they basically, if you're like an attacker in the regular non-virtualized network, basically they provide connectivity into the virtual overlay network. So basically, this is also very interesting to look at. However, setting this up would have required to set up a vCenter, configure that, pair everything with the vCenter. Not sure who has ever done that in the VMware space, but it's a lot of additional work, especially if you have such an experimental setup as we did. Then NSX has actually container support, so you can basically extend your virtual network onto the container level. There's like Kubernetes plugins that you can use, and I don't even have an idea how they implemented that yet. So it sounds reasonably complex to me, and probably another fun attack surface to explore. What we also did not look at, and I think it's probably less relevant, but it's the internal attack surface. So assume you like compromise one of the management systems. The services run as like low privileged users, so that's definitely a good thing. But once you compromised one of the management systems, you of course want to perform privilege escalation, and we did not look at that yet either. So what did we do? We analyzed the attack surface as described here. I know it doesn't seem like that much, especially when there's no cool vulnerability to present, but even if there would be a vulnerability, the presentation would have been exactly the same, because I usually like to give you a very good idea on how to find vulnerabilities, and this is the typical process that we used in other assessment projects. What we have done as well is, of course, like in order to get the debugging setup to work, we also like traced certain packages through the kernel modules, but like the combined size of those kernel modules is probably 7 to 8 megabyte. It doesn't sound like very much, but in terms of like CPU instructions, that's a lot of stuff. So what we also did is building this analysis methodology, which was also more work than we are happy to admit. And then we did basically some, let's say, due diligent assessment on the back end. So, for example, all the network communication that is happening on the control planes and so on is properly encrypted and authenticated. We checked the big Java applications for calls to deserialization functionalities. Unfortunately, there weren't any. That would have been a nice other quick win. And we provided a fuzzing setup to be able to inject packages there, provide some basic information on how to perform actually dump fuzzing there. So the future work, obviously the kernel modules are the main priority. I already ranted a little bit, okay, that's a lot of code to cover, and the point is it's also like rather difficult. If you want to only do that in a static way, it's a lot of stuff to cover. You need to find the entry points, like which data structures are coming in from where. I mean, this would be some internal attack surface talk that you can do just about the kernel modules. So we need to rely on dynamic analysis here. You won't really be able to inspect the data flows within the kernel modules, and then you won't get anywhere. However, of course, we've done spot analysis there. The most interesting part is that the tooling work that needs to be done here. So basically, those are proprietary kernel modules. They are reasonably close to Linux kernel modules. So there's not that much tooling available in order to fuzz kernel modules where you don't have the source code. I mean, there's not that many kernel modules available where that is the case. So what we're currently working on is export, let's say, the state of the ESX kernel module via this remote debugging session, and then use this as input for AFL Unicorn, which is probably at the moment the best way to go to perform some more coverage analysis of the kernel modules. Other ideas, we actually have an internal system that was built with this very scenario in mind, where we basically have a hypervisor, like virtual machine introspection based control flow analysis. Like one of our fellow researchers implemented that for the Open vSwitch within Xen, which then again was running virtualized in Xen, and then we collected trace flow data for the code. We definitely want to try that, maybe particularly with the KVM modules there. This might be another very good way to get like better code coverage analysis here. What's also interesting, there was a talk just this week at hack.lu on hypervisor level debugging, benefits and challenging, and he also provided some methodologies on how to analyze kernel modules, closed kernel modules from the hypervisor in a more efficient way. So this is definitely something that we need to look into. So also here, it's more of a methodology challenge. We could, of course, just stare for several weeks at the code, but that's always a time problem. So another interesting part is the software distribution mechanism from the NSX Manager update repository. That is also located in that isolated management plane network, so not the most interesting attack surface. However, if that would be like unauthenticated software updates, that might be a very, very easy way to inject code into the overall ecosystem. Then as well, I mentioned that earlier, the lab functions need to be extended in order to analyze all functionality. I think we're coming to an end here, which is good because we're on the last slide. So, concluding this talk, there were no low-hanging fruit or inherent architectural flaws that we could identify in VMware NSX. In fact, if you keep the management network isolated, there's already a very, very good attack surface reduction in place. There's a very good attack surface reduction in place. Then, I mean, obviously we still have the kernel modules, but if you want to offer functionality, you need to implement it somewhere. And even though I said it's like, let's say, up to 10 megabytes in kernel modules, that's not the most horrible thing I've seen. The biggest, like, let's say, network appliance related kernel module I saw was 120 megabytes. So the kernel modules seem to be at least implemented in a somewhat efficient way. What I hope we could provide, even if it's not a cool vulnerability, I hope we could provide you an overview how you could tackle research on VMware NSX. We would be very happy if someone else is jumping on there. There's enough stuff to cover that will be challenging time-wise. And I hope we could give you some insight into the attack methodology when you tackle such a large, closed, complex system as VMware NSX. And this methodology can certainly be adapted for other areas like network appliances or any other type of appliance. So that would be the conclusion. Thank you for your attention. Obrigado.